Hi, this is our second video tutorial on the Hydro module in Shape version 5. We are going to start with the Supernova model that we have used in our first tutorial and add some complications to it to make it a little bit more interesting and illustrate some of more features of the Hydro module and how to render objects. We open our recently worked on Supernova tutorial project, which is being loaded, and here we have three objects: the ambient medium, the explosive initial condition, and the rendering object. Now we want to add a torus object. We click on the torus primitive, go to one of the top viewport and drag out the object. Now our Supernova is going to overrun this high density object. We are going to set the density to a high density complex distribution. Let's change the radius a little bit to 3 and 4 and 5. Okay, and change the name to torus. Now we're going to first copy the ambient medium modifiers, so it is exactly the same as the ambient medium. We have a hydro, a density, a velocity, and a pressure modifier. We're going to select them all by first selecting the top modifier and then shift select the bottom one. We go down and then click on the copy button. Now we can go to the torus and click on the paste button and select copy, confirm. Now we have the same modifiers in here. We delete our two original modifiers in here. Well, maybe we can keep the density modifier, delete the temperature, and now our original density is going to be our texture modifier, texture density, that we are going to multiply our original density with. Now for that we are going to move the texture density down, okay, and change the operation setting to scale. Now open the texture editor, add a sparse convolution texture. A suitable size or scale of this texture is 1.5 times 10 to the 15. Change the exponent to 25 or so and the frequency to 3. Now we have a complex structure in this torus. It scales the original ambient medium by that structure. And for visualization of this, we can go to the render module with a grid size of 128. We render this. So now this is the structure, the high density structure into which our explosion is going to run. And we should save that setting into a new file. Go to the Hydro module and check the values. The grid size is okay, 128. It's not set to resume. Our flow parameters, times is the old time, which is probably okay. Cooling is enabled. Gamma values is reasonable. Eta, the diffusion, is okay. Minimum temperature of 10,000 degrees. we could set this to 1000 so the clumps that are being overrun can cool further. And that's about it, I think, and we can give it a go. Save again and run calculate. Now wait, make sure you have enough memory to run this for this resolution. Don't do this on a 32-bit computer, and make sure you have more than 10 gigabytes or so RAM that is also assigned to the Java to shape. Here we have a total megabyte up to 19 gigabytes, which should be enough. But if you have a small machine, make sure you do the setting of the virtual machine memory that can be accessed to that kind of values, or 10 at least, and try and see how high you can go in resolution of the simulation in here, the grid size. Okay, now we can start running it by clicking on the calculate button. Initializing the background, and as soon as the status numbers of time step and time step length appear, the simulation runs. Now we have our initial condition here, which looks rather weird. Let's check the camera setting. This may be unsuitable. We enable that. Orthographic. I know what we have. There is a problem, and I leave these little problems. Now we have our initial condition is clumpy, and we need to change the torus hydro modifier to, instead of background, to initialize. So it's just an initialize object and is confined to this volume region of the torus. Otherwise it initializes the whole volume with these conditions, which is not what we want in this case. So let's go back to the simulation and restart. Now this looks better. This is the probably the pressure. Okay, here we are. Now there's still a problem here. The torus is actually lower density as the ambient medium, which is because the texture actually takes the maximum value, and then every void and low density is actually reducing the density compared to the maximum value. Therefore we have to multiply our scaling by a large factor to get the right value. And I leave these little problems, startup problems, but in a simulation, so you're warned that these can happen. Actually, we're going to set this F0 value, which goes with the scaling density texture, to something like 50, and then go back to the hydro, restart the calculation. Now we have our high density torus compared to the low density environment. This looks much better, and this is the pressure, which is initialized at a high value only in the inner region where the explosion happens. Now this is going to run for a while, and we can change the camera setting maybe in the meantime to have a better view of the density distribution. We go to the camera tab and open the edit image dialog and see what the normalizing does. We could use a square root, apply. Yes, that looks much better. Now we can see actually the explosion in the middle, the shell that forms around it. Now if we rotate this, we can see also that there are filters applied which select only the central plane and you can see that in here the filter tab. Here are two filters, of which probably the Y filter is disabled. Let's go to the filter module, and here we see these two filters. Yeah, the Y position filter is disabled while the Z position is enabled, and it cuts out a little piece of the whole domain. Okay, now we let this run for a while, and then in the meantime I will pause the recording, and we will see how it goes in a few minutes. Okay, returning to the simulations after about 5 minutes. Here we have the interaction region has now reached the dense torus, and as we look at click on one of these windows, we can see that in the camera tab the image size is set to 80, which is smaller than the actual simulation grid. So we set this to 128, which improves considerably the detail that we can see in the image. Similarly, we will do this in the pressure image. 128, it shows much better the detail. In the pressure image we can clearly see that the interaction is going on now. We will pause again for a few minutes. Okay, after a few minutes the interaction is now getting through the torus in the low density regions. Here we can see the density is increasing outside. These holes are being penetrated, and let's now see how we can use the filters in a useful way to visualize this a little better. We add a new filter for the speed filter, and then set the minimum velocity so we see only the interacting or moving parts of the simulations to say 3 kilometers per second, and add this filter to the simulation pre-visualization speed filter, and now the whole ambient medium is gone and we see only the moving regions. And we now exclude or disable the Z filter, so we can actually see the whole object that is moving. See, now we have a spherical volume roughly. Well, we see as we rotate the object that it's actually kind of bipolar, avoiding the region of the torus, which is expanding more slowly. It's included into the expanding shell. And let's now stop for another few minutes and then render this. Okay, back from the coffee break. It has advanced a little bit. Note that the supernova explosion becomes slower and slower with time, but how long your coffee break can be, or whether you have to wait for overnight, depends of course on your computer, how many cores this is running on. The code is parallelized and can run on several cores simultaneously, so it depends on that number, how fast your code is running, how many time steps it's going to do, and of course on the resolution, the grid size. Right, now let's inspect how our objects looks like. We have this bipolar structure with the torus in the middle, nice and complex. Now let's see how we can render this. We go to the render module, and here we still have the rendering of the initial torus, which we have to disable the rendering of the torus. We go select the torus object in the 3D module, go to the general tab, and here at the top we have this render property, which is set to mesh by default. we set this to null. So this object is not being rendered. We only want to render our explicit render object, which can be any type of object. All the others should be set to null rendering, and our render object is set to hydro, which then takes the hydro mesh and the hydro grid and uses it for rendering. Now let's render this. It is of course convenient to stop the rendering, the simulation before rendering, so they don't interfere and the CPU is not taken over by the simulation. So you click on this cancel the task button at the bottom left or bottom right, and now we can have a look at the rendering. Okay, here's our ring or torus now. We can see only the densest regions, so let's change the settings for the image properties. The grayscale we change to something like square root. Let's see. Yeah, square root should be okay. Maybe, yeah. Confirm. Now we have our shell around it. We go to the camera settings and set the angle to say 80 degrees and re-render. Now we see it edge on. Okay, let's change this again, maybe to power, and set the power to 1/4. Okay. Now we can see that the ambient medium is also included. We can change this by using our filters, which we already set. Go to the 3D module and apply these filters to our render object. Select the render object, go to the filters and add the speed filter. Select the speed filter in the drop down list and then add it. It should then appear in our filter list. This should change our rendering in a way that it takes everything out. Okay, the reason for that is that the speed filter is set to meters per second for the simulation, which works in meters per second, and we need a different speed filter in kilometers per second for the rendering. We will change this in a future version, so this is more consistent. So be alert to any changes in that. This we will call meters per second. Okay, go back here, and then we set this to 30 kilometers per second or 3 kilometers per second, and then redo the render. And there is still nothing. Oh, we have assigned the wrong filter now, of course. We go back to the filters, delete the meters per second filter, and add the kilometers per second filter. Okay, go back and re-render. Now it takes a little longer time because there's actually something to render. There we go. Now the ambient medium is filtered out and our object is here. Now there's no PV diagram. Why is that? Because our slit is too small. Go to the group and we see that the width and height are very small in our units. So we activate the move slit cursor button at the top, and then we can actually drag out the size of the slit if we use control Y. We click on the Y button, then the length changes. Okay, now we can actually re-render and get a PV diagram. There you go. Here we can see the brightest parts, which are the cells that are in the torus. Should also change the image adjustment properties from linear to square root maybe. Yeah, here we go, is our power, small power. There we are. Here's our complete structure. And we can see the individual cells here. We can add a resolution, say 20, which then smoothes this out, and here we clearly see the slow advancement, slow speed of the torus, which is overrun by the fast supernova remnant at more than 200 kilometers per second, and the torus is expanding only at a quarter of that speed roughly. The densest parts are still near zero. Okay, what else can we do with this? Like have a look at different quantities here. The gradient image, for example, which is red and blue shifted. The back of the torus is red shifted, the front is blue shifted. And we can, by clicking on, using this image function and the little tool button, we can change the configuration and what is actually shown. Instead of showing the velocity, we could show the temperature, which should be running from 100 to, I don't know, let's say, no, from 1,000, the minimum, to, let's say, 10,000. Let's see what that does. We re-render. And we see that in this range, we see only the cool gas, the high density cooling gas. So we should increase this to 10 to the 6 maybe. It should show the hot gas in red. There you go, the hot gas. Well, this is all still kind of cool. It's not that hot at all. So we probably are better off with 10 to the 5 as a maximum to show the distribution. Yeah, here you go. Here you can see the temperature distribution. If we do the same thing for the PV diagram, we can see which gas is moving faster and which one is slower. There you go, the hot gas, the cool gas is moving slowly and the hot gas is at many different speeds, projected speeds of course. Okay, that shall be enough for this video tutorial. We have seen how we can modify an existing simulation project by adding more complex structure to it, and then how to apply the filter bank, the filter module, to select different parts of the simulation for pre-visualization and for rendering, and then how to obtain the basic renderings including image and PV diagram using our basic renderer in the renderer tab. Thank you.